Hi, this is Maggie. In this video we're going to talk about sprite motion that uses floating point calculations. I'm going to start by showing you listing 10.6, which is a bad example of floating point calculated motion. I've changed the speed from 3 to 2 so that the errors are a little easier to see. I can press the arrow keys to turn the car. Now notice when I turn the car, at some angles, it seems to slide sideways. This is not a natural feeling motion unless the car is on ice. We expect the car to move forward in whatever direction it is pointed and not slide sideways. And here's listing 10.7 running. Now the tight turns look slightly awkward because the image is being rotated around its center and because it's being rotated by 10 degrees each time, making that a smaller increment looks better, but the car always moves forward in the direction it's heading. Let's look at the bad code. The code for 10.6. Both examples are similar, but this one is simpler, so I want to start here and explain what's wrong with it. Here's the car sprite, and you can see some fields that are in the car sprite. Speed and angle. Does that give you a hint about the kind of motion being implemented? If you guessed vector motion, you're correct. The sprite also has fields to store the raw image, which is a copy of the image that will be rotated. Always rotate from the original copy of an image. And a Boolean moving, because the user can stop or start the car by pressing the spacebar. So this Boolean keeps track of whether the car is moving or not. And in init, we set the raw image, set image to a non-rotated version of the raw image, randomly generate a location for the car by locating its rectangle. We set its speed to 2, although in the original it's set to 3. Set its angle to 0, or pointing right, and set moving to false. So that is our start state of the car. It begins at a random spot on the screen, facing right, and not moving. Let's go down to the game loop. This is a really simple game loop. We process left, right, and space keys. The space key sends the stop or go message to the car sprite, which simply toggles it between moving and not moving. We process left and right key presses by sending the change angle message to the car, and then below the event processing, we clear, update, and draw. So all the work is done in change angle and update. Let's take a look at those. You can see change angle takes one parameter, which is a Boolean. It gets false for a left key and true for a right key. So in change angle, that Boolean is called increase. And if that's true, we add 10 degrees to our car's angle. And if it's false, we subtract 10 degrees from our car's angle. So in update, we calculate a dx and a dy using vector motion. Dx is the cosine of the angle multiplied by speed, and dy is the sine of the angle multiplied by speed. These are the amounts by which the x and y location of the car should change based on its speed and angle. We then rotate the car image based on the angle, and in doing that, we get the x, y coordinate of the rectangle, and we are going to set it back using that x, y coordinate rather than simply adding to the rectangle. This is because rotating will change the rectangle of the image. So we need to find its center, rotate the image, and then set the new center to the old center. We set the center to the old center, but with dx and dy added. So what's the problem? The problem is that the rectangle uses integers, not floats. So every time we move the car a little bit, we add a little bit of error because we're chopping off the floating point part from its location. And that error adds up over time, and it's enough to make the motion look really weird and give us that sliding effect. Now let's look at listing 10.7. The way we fix this is actually really simple. We add two more fields to our object, x and y. These are floats. We can't trust the rectangle to keep the exact location of our car because it's truncating off the floating point part of the location, losing critical information 30 times a second. So what we do is keep track of the location ourselves and always set the car's location using our floating point variables. So everything else in this sprite is basically the same as in listing 10.6. except that we don't get the center x and center y from our rect because we don't trust it. We always add dx and dy to self.x and self.y, and we locate the car using those coordinates. Now, this program is using top left to locate the car. I think it actually looks a little better if we use the center attribute of the rect. Possibly because the car is rotated around its center. I changed the center in the initializer and an update and ran it again, and I do think that looks a little better. Otherwise, the car is sort of driven by whatever part of it is at the top left. So the lesson here is if you're going to use vectors to calculate the location for a sprite, or any other sort of calculation that will result in a floating point result, then you should store the location of the sprite independent of the sprite's rectangle, and rely on your own stored locations, not the rectangle's location, when performing location calculations. Try experimenting with vector motion in a sprite of your own until you're comfortable applying this kind of motion to a sprite. Have fun with it.